Hi, I'm Deepak Khurana. I work at Qruise, and today I'm going to walk you through a notebook where we will set up a diamond quantum processor using Qruise Toolset, and then we'll also optimize quantum gates on such a processor. The video is divided into two parts. In the first part, I will briefly discuss what is a diamond quantum processor, and in the second part, I will set it up using Qruise Toolset. Let's begin. So what is a diamond quantum processor? Imagine a diamond crystal where we replace few of the carbon atoms with nitrogen atoms. Now since there is a difference between valency of carbon and nitrogen atom, it leads to creation of a defect in the crystal. This defect is called nitrogen vacancy center or NV center. This NV center has very useful properties like it has long spin coherence times, it is biocompatible, and it can be operated at room temperature. All these properties combined together make it a very attractive candidate for quantum technology applications. Now for quantum computing applications, the qubits are the nuclear spins of nitrogen and carbon atoms, and NV center only act as a bus to initialize, read out, and perform gate operation on these nuclear spins. Now let's discuss the energy level structure of this system. The NV center is a deep defect inside the diamond band gap, and the ground and the excited electronic levels are spin triplets. There is also a metastable state which is spin singlet. When we shine a laser beam which matches the energy gap between ground and excited levels, the NV center gets excited, and if it's in ms equal to 0 state, there is a higher tendency to just decay back to ms equal to 0 state. But if it's in ms equal to plus minus 1 state, there is a higher chance that it will go through metastable state, stay there for the lifetime of the metastable state, and then eventually decay back to ms equal to 0 state. This fact is used to initialize and read out the spin state of the NV center, because starting from any thermal equilibrium population, the NV center, given enough radiation time, always decays back to ms equal to 0 state. And since ms equal to plus minus 1 state spends some time inside the metastable state, the fluorescence emitted by NV center becomes spin dependent. The energy gap between ms equal to 0 and plus minus 1 state is equal to the zero field splitting, which is 2.87 gigahertz, and then if you apply external magnetic field, we can also lift a degeneracy between ms equal to plus minus levels. For quantum computing application, we usually limit ourselves to these two levels, ms equal to 0 and ms equal to minus 1, by applying a very high magnetic field and energetically isolating the ms equal to plus 1 level. Now, the NV center is coupled to the nuclear spin, which further splits the levels of the NV center. For example, here I'm showing the splitting caused by two nuclear spins surrounding the NV center, and it leads to total of 8 levels. Now the subspace corresponding to ms equal to minus 1 is called computational subspace, and this is where all the single qubit gates on nuclear spins are realized. Ms equal to 0 space is called the auxiliary subspace, and it only participates while we do multi-qubit gates. Now how to do universal quantum computation on the nuclear spin resistor? For universal quantum computation, we need to do both single qubit gates and a CNOT type of gate. Now, in this processor, the single qubit gates are simply realized by performing rotations on the nuclei inside the computational subspace. To do a CNOT type of gate, we first have to do a controlled C gate, which is basically a controlled phase gate, where we apply a 2 pi microwave pulse on NV center when the nuclei are in 1-1 state. When you sandwich such a CZ gate between two Hadamard gate on the nuclear spins, it realizes a effective CNOT gate. You can look into the detail of this CNOT gate inside this paper. Now let's move on to the Hamiltonian of the system, because this is what we will be implementing inside the Qruise toolset. So the full Hamiltonian of the system is described by this equation. Let's discuss each term one by one. The first term is due to the zero field effect, where T is the zero field splitting and S refers to the spin operators of the NV center. The second term is due to the Zeeman effect, where gamma E is the gyromagnetic ratio of the NV spin and B naught is the externally applied magnetic field. The third term corresponds to the applied control field, and the next term is due to the hyperfine interaction between electron and the nuclei, where A is the hyperfine coupling tensor. Here I refers to the spin operators of the nuclei. The next term is due to the quadrupole effect on the nuclei when the spin of the nuclei is greater than half. The next term is due to the Zeeman effect on the nuclei, and the last term is the control drive applied on the nuclei. In this notebook, we will implement and optimize single qubit gates on the nuclear spin resistor. Now, as we discussed before, the single qubit gates are realized inside the computational subspace by the rotations on the nuclei. Now, we will further simplify the Hamiltonian we just looked at by two more approximations. The first one is the secular approximation, which is valid when a very strong magnetic field is applied along the z direction. The second approximation is that we'll only consider the nuclei which are partially misaligned to the NV axis. After this approximation, the Hamiltonian simplifies considerably and looks like this. This is a standard textbook Hamiltonian of uncoupled spins, where omega I is the transition frequency or the level gap of the ith nuclei, and it contains the effect of both applied magnetic field and the hyperfine coupling. The drive can be expanded like this, where the frequency of the drive is omega, its phase phi, and the shape envelope omega t. Now we will go to the rotating frame of the drive and we will apply rotating wave approximation. After that, the Hamiltonian looks like this, where delta omega I is the detuning of the ith nuclei from the drive frequency. Now let's set up the Hamiltonian we just discussed for single qubit gates using the Qruise toolset. The first step is to set the parameter of the system. Now here we will consider NV spin coupled to only two nuclei. One of them is N15, the other one is C13. We start by setting up the magnetic field, which we set up to a very high value so that the secular approximation remains valid. The next is the hyperfine coupling, then the gyromagnetic ratio of each nuclei, then the transition frequencies, and then finally we set up the detuning of each spin from the drive frequency. Here we will consider that the C13 spin is on resonance and the detuning on N15 spin is the difference of the transition frequencies. Now the next step is to define the Hamiltonian components. So here in our Hamiltonian we have two components. One of them is the detuning part and the another one is the drive part. Now for the detuning, we can use the Qruise spin class, where we have to specify the dimension of the spin that we are trying to create. For example, here we are creating a C13 spin, which is a spin half system, so the dimension of the Hilbert space is 2. Apart from the identifiers, we need to also pass a parameter, which is the offset or the detuning that we just defined. In Qruise toolset, the parameters are usually passed as quantities, where you can mention the value, the minimum and the maximum bounds, and also the unit of the quantity that you're trying to make. Now, similarly, we can specify the N15 spin, and then we go on to the drive component of the Hamiltonian. Here, we can use the drive spin class inside the Qruise toolset, which realizes a term like this, where you can specify the direction of the drive and the signal which is coming from the control stack, and then also the gyromagnetic ratio of the spin. So here we are doing that. This is a drive applied on the C13 spin. So again, apart from the identifier, you have to mention to which channel or to which spin this drive is connected to. Here it is connected to C13 spin, and then we can mention the drive direction. For example, here we are creating a drive in the X direction, and then again the gyromagnetic ratio is passed as a quantity to this class. Now similarly, we can define a drive on N15 spin. Finally, after defining the two Hamiltonian components, we just collect them into a model class. Here in the model class, we have to mention the subsystem and the couplings. In the subsystem, we have two spins, which is C13 and N15, and in the coupling part, we are creating a coupling of the spin to the drive. Let's say if there was another type of coupling, let's say dipolar coupling, then we will use Qruise coupling class to create the coupling component first and then mention it here. Here in the model class, you can also specify which basis you want to carry out your simulation. Here we will carry out the simulation in the rotating frame of the drive, and so we can set the rest frame to false. And also in the Qruise toolset, you can specify in the model class whether you want to include the effect of the surrounding environment or not. So in Qruise Toolset, the effect of the environment is modeled as a Lindblad equation, and you can specify if you want to switch that open dynamic or open system dynamics on or not by this parameter. Now we have defined the Hamiltonian components. Now it's time to define the control field itself. Now in Qruise Toolset we get a lot of freedom. In here we can define the whole control stack, which includes a local oscillator, the arbitrary waveform generator signal, then digital to analog converter signal, and then finally everything is mixed inside a mixer. Now this offers a lot of advantages, because if you want to introduce non-ideal behavior into each of the device, then you can do that. But here for this notebook we will use the simple generator class, which assumes that all of the devices are ideal. For the simple generator class we have to pass two parameters. The first one is volt to hertz converter. Basically this parameter says that how much voltage on the control device will correspond to what magnitude of the control drive. So here, since our drive is multiplied with gyromagnetic ratio, so basically our drive is scaled by the gyromagnetic ratio, so we will set our volt to hertz converter to 1 divided by the gyromagnetic ratio of the spin. And then we have to specify the resolution of the AWG. Here the resolution of the AWG is 1 divided by this number, then the AWG resolution will be 1 nanosecond. Then finally you pass this parameter to the simple generator class, and it creates a output like this. Omega t is the pulse shape, omega c is the carrier frequency, omega sp is the single sideband frequency, and phi is the phase of the drive. To set the carrier frequency, we can use the carrier class, where the carrier frequency is passed off as parameter. Since here we are doing simulation in the rotating frame of the drive, we can set carrier frequencies to 0. To set the shape of the pulse and single sideband frequency and the phase of the drive, we will use the envelope class, where the shape of the pulse is passed as in phase parameter, and then the phase is passed as xy angle parameter, and the sideband frequency is passed as frequency offset. Now here we are using a piecewise continuous shape, which has previously been used in NV Center processor for sensing and quantum computing, error correction, and many more things. Now next, after we have defined the Hamiltonian component and the control stack as well, now it's time to define what we want to do on our quantum processor. What's the instruction? So here we want to perform single qubit gates, and as an example we choose to perform a 90x pulse on the C13 spin. Inside Qruise Toolset we can do this via instruction class, where you have to specify the name of the gate, the target spin. For example, the 0 index here indicates the C13 spin, start and end time of the gate, and then the drive channels. And then further, using the add component function of the instruction class, we can also add the shape and the carrier frequency of the drive. Now that we have defined the control stack, the model, the Hamiltonian, we can combine them all together inside a parameter map, and then pass it on to the experimental class to instantiate experiments and calculate the propagator. Here, to calculate the propagator, we use the piecewise continuous propagation method. Qruise provides support for multiple type of propagation methods. After defining the experiment, it's time to calculate the dynamics and visualize it. First, we calculate the propagators using the compute propagator function inside the experimental class. Then we define an initial state and the sequence. In this case, our sequence is simply the gate we are trying to simulate. After defining the initial state, we can apply the propagator to initial state and then draw them using the draw dynamics function inside the experimental class. Under ideal 90-degree rotation, the population of 0 and 1 state of C13 spin should equalize. But as we can see here, we are far away from reaching that point because the pulse shape initial guess that we took was a bad one. We can draw this pulse shape using the draw function inside the generator, and we can also specify output of which device we want to look at. Here I'm looking at the output of the AWG. Similarly, we can also view the Fourier transform of the pulse shape using the draw spectrum function inside generator. Now let's move on to optimization. We start by setting up the optimizer, and as a first step we have to define a opt map. The opt map is collection of parameters that we want to optimize. For example, here we want to optimize the amplitude of the piecewise constant pulse, and this is what we have set up here. Now, the whole information about the optimal control is contained inside this optimal control object, and apart from the opt map, it takes two more important parameters. First parameter is the cost function, which is minimized in the each run of the optimization. Now, we set unitary infidelity function as our cost function, which is nothing but 1 minus the trace distance between ideal and the simulated unitary. Now, the next important parameter is algorithm. Here we work with a gradient based algorithm, but any type of gradient free or gradient based algorithm is not a problem. Now, after setting up the optimizer, we are ready to run it. First, we have to set the experiment for the opt object, and then we can run optimize control function to start the optimization. After that, a nice figure will appear which tracks the progress of the optimization. We start with a very bad infidelity of 0.26, and then eventually we reach a very high fidelity after a few iterations. We can look at the best fidelity using the current best goal call in the opt object, and we can again draw the dynamics using the draw dynamics function, and we can see that the optimized pulse has been able to achieve very close to the ideal dynamics, where the population of 0 and 1 level of C13 has been equalized, and the population in the levels of N15 spin has gone back to 0. There was a sudden increase in the population of the N15 levels because of the detuning. Now we can again draw the pulse, but as you can see that there is not much difference visually in the unoptimized and the optimized pulse. But when we look at the Fourier transform, it reveals that the optimized pulse has been able to achieve the higher fidelity by scaling the amplitude of the DC component. So that's it from the optimization for the single qubit gates on a diamond quantum processor. Stay tuned for the multi-qubit gates and optimal control on other type of qubit modalities. Thank you very much.